All right, chemistry team, coach coming at ya. Let's do this continuation of this crazy madness called quantum mechanics. Ultimately, just trying to figure out where the heck is this crazy electron and what's its energy. We have to go through all of this stuff to do it. So we went through Schrodinger's equation, showed how crazy that is and how just that brain of his just being able to solve that was nuts. The solution to the Schrodinger's equation, of course, for an electron standing matter wave in 3 dimensions gave us what were called orbitals, right? Right. So we get all these different, and we can have n equals 1, n equals 2, blah, 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 blah. But the problem is, when you do it for that one-dimensional particle in a box thing, you only need one quantum number. If you do it in 3 dimensions, you need 3 quantized numbers to characterize each specific orbital, which is kind of, think of an orbital as a seat an electron can sit in. So you've got the nucleus, and you've got this 3-dimensional sphere of space around it that we carve up into specific regions with specific shapes containing 95% of, sometimes 90%, but I'm going with 95% of the electron probability. And we call that electron seat an orbital. That's where the electron charge is spread out in. All right. And it's hard to find. It's hard to transcend a quantum behavior to a classical or macroscopic analogy. But my whole family's filled with musical theater diehards, right? That's my wife was trained in musical theater. All three of my daughters are in musical theater. Will my son go into it? I don't know. I did some musical theater, nothing professionally like my wife did, and nowhere near the caliber of what my daughters did. But I did a little bit of musical theater myself back in the day. Princess and the Pea was the jester, but loved singing and entertaining. But my wife loves to go to these shows. I like the majority of them. My kids love them, so we'll go down to the Orange County Theater Performing Arts. Sometimes some more local ones, community theaters. We don't care. We just love going to see shows and stuff. But with the nicer theaters, you walk in, you got your tickets, and it's all dark. You're heading in there, and we head up, and there's somebody there with a flashlight, and they take a look at your ticket, and I'm like, all right, I walk in the front doors, and we're there with my wife, all dressed nice. Going to the theater, this is so wonderful. Gonna go see, ABBA or Les Mis or Hamilton or something, right? Haven't seen Hamilton yet live, or Phantom of the Opera, whatever it is. And then the person, shines their light and goes, you're up there. I'm like, oh, because there's like the ground floor, I think it's a mezzanine nosebleed, things like that. So like, okay, cheapskate, you're up in the nosebleed section. Oh, I'm in level 3, so we got to climb up all the stairs and get in there. Can I just sit anywhere in any seat I want in level 3? No, there's another person when you open the door, clicks on their flashlight. You're in row LL in the back. Oh man, I wanted to be in the front so I could look over the railing, and didn't, because I'm height challenged, so I can't see over these people sitting in front of me. I'm like, come on, they'll got my spiky hair, makes me 5'7" rather than 5'6.5". So we got to go back, to one of the back rows. Can I just sit in any seat I want in that row? No, you're in seat 13. I don't even know if they have seat 13. Right in the middle, and you're not climbing over people's knees. Oh, can I be on the edge? So, how many pieces of information did it take to find my seat? I needed a level, I needed a row, and I needed a specific seat. So I needed 3 pieces of information to find where I'm sitting. Oh, interesting. Okay. Well, same in the quantum world. We need 3 pieces of information, 3 quantum numbers that tell us where that electron seat, aka orbital, is. Let's look at them. Let's look at the quantized restraints put upon those and kind of what they mean. I'll do my best to kind of relate this to a macroscopic thing. What does that mean in our brain? How can we think about what that quantum number really means? Let's do it. All right, the first or principal quantum number, I think, is the easiest for us to comprehend. This is the one that kept popping up in these one-dimensional particle in a box, scenarios we were talking about. That you kept seeing this n come into place. N can be 1 or 2 or 3 and have to be a positive integer, greater than 0. Kept popping up, allowed the certain types of wavelengths for these waves to exist and not destructively interfere with themselves. It's what creates the quantized nature of it all. So think of it, if you're thinking in polar coordinates like we showed, it's the radial electron density distribution. So take the nucleus, right? So let's say we got the nucleus here, and just take one angle and just go out from that nucleus and go, well, are there electrons there? What's the electron? No, yes, no, yes, no, yes, no. And you're just moving along from here out to infinity and go, are there electrons? So that's the radial electron distribution, which we can think of, right, describes the size of the orbital. And obviously, it's similar to the Bohr one, size equates to energy in this case, right? So the higher n is, the further away the orbital is, or the electron is from the nucleus, if there's an electron in there. Or remember, this is a seat. Doesn't mean there's an electron in it, just means it's a quantum seat somewhere around the nucleus, right? So the bigger n is, the bigger the orbital, the further from the nucleus, and the higher the energy. Remember, we defined infinity as 0 with the Bohr model. A separated electron was 0, and then as you get closer and closer, it lowers in energy and becomes negative. So same idea. As you get further out, you get to larger orbitals, higher energies. There you go, right? Now, we can relate this, in our everyday world as an electron level or a shell, right? A certain distance from the nucleus. So you'll hear us use the principal energy levels, like on the periodic table, n equals level 1, level 2, n1, n2, or row 1, row 2, row 3, row 4, right? You can almost equate those as the principal quantum number energy shell levels or electron shells. See what I'm saying there? Now, allowed values, this is what we've been doing this whole time. All integers greater than or equal to 1. It can't be 0. That means you're in the nucleus, right? It also means that electron's at rest, and it's not at rest, okay? It's hard to have angular momentum when you're at rest. So it can be 1, 2, 3, 4, all the way to infinity. Infinity meaning, boop, the electron has left the building. It's no longer on the atom. You now have a cation. All right, I think that one's pretty straightforward. Let's get to the weird ones that deal with those two angles, right? When you look at polar coordinates, theta, and whatever the heck that other one was, let's ponder those and how that impacts what these orbitals look like. Ready? Let's look at the next one, the second quantum number, the angular momentum quantum number. We give that a little cursive L there, lowercase cursive L, which completely depends on the value of n. So we're taking n as kind of like the big umbrella, and then we're breaking that up into smaller chunks, and then breaking that up into smaller chunks. It gets a little more specific. All right. So if the principal quantum number n was the radial electron distribution, think of the angular momentum quantum number as the angular electron distribution. So say you take the nucleus, take a point from that nucleus at a set radius, and just go around in a circle around the nucleus and plot the electron density or probability distribution, right? So that kind of gives you the angular electron distribution. So that will ultimately describe the shape of the orbital. Is it a sphere? Is it not? Those kinds of things, right? And you're going to see some weird shapes come out of this. Oh, they get crazy. And I guess if we want to think of it, we can think of it as relating to the subshell or sublevel. So if n, the principal quantum number, is the shell, or the whole level, L would be the breakdown of that into smaller chunks. And the further you get from the nucleus, the more space there is, the more we need to carve it up into smaller chunks. It's like if you go, like at the show, you got the ground level, mezzanine, and nosebleed. Well, if you pick one of those levels and go in there, that's broken up into rows, right? So it's just broken up in a certain number. And the bigger the level, the more rows you have to break it up into. Right? Oh, I spelled wrong. Integers. So allowed values, all integers. I was like, integers. All integers from 0 up to n minus 1. So you can actually have a value of 0 for the angular momentum quantum number L. You can't for n, but you can for L. So it depends on what the value of n is. And the total number of values, just mathematically, will be n. So if n is 2, you'll have 2 values of L. If n is 3, you'll have 3 values of L. Let's play with the numbers on the next board and just show you what different values. I'll give you different values of n, and we'll calculate the allowed values of L and what those mean. All right, well, see if you can do this. You probably learned this. Well, I don't know if you did quantum. I don't typically teach quantum numbers, all of them, in introductory chemistry, maybe in high school, depending on who you had for a teacher. You definitely learn what n is, but you might not learn what the other quantum numbers are, like the angular momentum one. So let's say we have n equals 5. So we're at that 1, 2, 3, 4, 5. So we're way away from the nucleus. Really big, right? Lots of space, right? If you got a sphere, it gets bigger. The further you get, the more volume you have, the more space you have. So we have to carve that up into more and more subsections or sublevels. So for the n equals 5 level, that's a lot of space. We're going to hack that up into 5 subsections or sublevels or subshells. So what are the allowed values of L? Okay, as you remember, L values are all integers from 0 up to n minus 1. So we start with 0, okay? So we can have L equals 0. Let's do this in red. We can have L equals 0. We can have, now what's n minus 1? N minus 1, what's n? 5? 5 minus, oops, I did that wrong. 5 minus 1 equals 4. So we're all integers from 0 to 4. So we can have L equals 0, L equals 1, L equals 2, L equals 3, L equals 4. There you go. That's not too hard, right? And how many? 1, 2, 3, 4, 5. 5 values, right? The number of the values of L is equal to n. So we have five subsections. So we take this huge energy level and take a quantum axe and go whack, 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 and break it up into 5 sections, right? The further from the nucleus, the more sections. The closer to the nucleus, the fewer subsections you have. Now, I'm going to do the shapes on the next video. What I want to do is give you their special terminologies we have for these, right? For the subshell. Let's do this in black. So for L equals 0, we call that the S subshell, or the S sublevel, I guess you could say. For L equals 1, we call that the P. Now I'm going to do subshell and sublevel just to show you that they interconvert. It's the same thing. I don't care which one you use. And these letters have, names to them, I'll tell you. So L equals 2 is the D subshell. You know where this is going. I know you know these. L equals 3 is the F subshell. So you've probably heard of the S, P, D, and F. They have characteristic shapes to them because this is the shape. We'll look at the shapes on the next video when we do this. Let me erase this. Now these come from, you don't have to know this, but it comes from experimental terms. A lot of people go S, spherical, right? Those P, propeller. No, that's not what they stand for. So the S stands for sharp. It's the lines they get when they do spectroscopy. This stands for principal. D is, I think, diffuse. And F is fundamental. I usually do F for freaky because they're freaky weird. S is pretty simple. We'll find out they are spheres, right? P look like, like an hourglass typically, or a propeller. So commonly in introductory chemistry, I'll go S, think of sphere, P, think of propeller. And we usually don't even do D and F type orbitals in introductory chemistry. We're definitely going to do D in my class. F I'll show you, but we're not going to deal with a lot of F orbital because we don't deal with that chemistry very often. But anyway, and then from that point on, it goes to G, and they just follow the alphabet. So it goes S, P, D, F for 0, 1, 2, 3, and then G, L equals 5 would be H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V. There's no elements that have enough electrons to exist in those. Anyway, so we really only worry about these first 4. So I'd like you to memorize these if you haven't already. So L equals 0, an angular momentum quantum number of 0 is equivalent to an S subshell. L equals 1 is a P subshell, L equals 2 is a D, and L equals 3 is an F subshell. So you have this huge energy level or electron shell broken up into a certain number of subshells, which gives you the shape. Fumbled my pen. let's look at the third quantum number. All right, our third and final quantum number to relate an orbital. Turns out there's going to be a fourth one later, but it relates to the electron specifically, not to the orbital itself. So really there's 4 quantum numbers we're going to be dealing with, but only 3 used to characterize or identify a very specific orbital or electron seat in 3-dimensional space somewhere about a nucleus. All right, so we've got the principal quantum number n, the angular momentum quantum number L. Now we've got the magnetic quantum number M sub L, so obviously this depends on L. L depends on N, M sub L depends on L, so they all depend on each other. So imagine, again, you've got a big level, a principal level, then we hack that up into sublevels. We take each sublevel and hack it up into smaller bits called orbitals or seats. So you've got the ground, mezzanine, nosebleed, find your level, broken up into rows. Those rows are broken up into seats. Yeah, obviously human seats, but here we're looking at quantum electron seats, which are kind of weird because you can have 2 people sit in each seat in the quantum world. As long as they sit weird. All right, anyway, so the magnetic quantum number looks at the orientation in 3-dimensional space about a nucleus of a specific shape. For example, if we have L equals 1, which are these propeller-shaped, right, or hourglass-shaped things from the angular momentum quantum number. Well, how many ways can you orient that in space? X direction, Y direction, Z direction. So there's 3 ways to do that. So there's 3 orientations of that. That's kind of what that means. And then each specific value you get of M sub L, the magnetic quantum number, characterizes a very specific orbital or electron seat. There we go. This is what we're after. So the number of allowed M sub L values for a given L value, all right, we got a sublevel. How many seats can we break it up into? How many orbitals? Well, the number of allowed M sub L values is the number of seats, electron seats or orbitals in that sublevel or row. Right? And now here's the quantum rules here. What are the allowed values for M sub L? For M sub L. All integers between negative L and positive L. We'll do some examples on the next board, right? But for example, if L's 1, you could have -1, 0, and +1. Okay? So the total number of M sub L values or orbitals for a given sublevel is 2 times L plus 1. So if L is 0, you'd only have 1 orbital in that. And that would be S, right? So for L equals 1, 2 times 1 is 2 plus 1, you'd have 3 seats or orbitals in an L equals 1 or P sublevel. Let's do that on the next board. All right, some practice for you. So for each of the following, determine the number of allowed M sub L values, right? So remember, the number of values is 2 times L plus 1. So you should know how many answers you should get, but you can just figure it out from the mathematics. So I recommend that you just pause this and do it for me if you haven't done it already in the past. So let's just take the 4 most common sublevels, right, or angular momentum quantum numbers. L equals 0, L equals 1, L equals 2, and L equals 3. Now remember, L equals 0 is characterized as the S sublevel, sharp. L equals 1 is the P sublevel, principal. L equals 2 is the D sublevel, diffuse. And L equals 3 is the F sublevel, fundamental. Sharp, principal, diffuse, and fundamental. Not important that you know that. All right. Here we go. Now, again, we need to know the rules. You have to have those rules memorized. All right? So what are the allowed values of n? All values, all integers equal to 1 or greater. 1, 2, 3, 4, 5. Can't be 0. What are the allowed values for L? All integers from 0 up to n minus 1. What are the allowed values of M sub L? All integers from negative L to positive L. They depend on the one prior to it. N is the big umbrella. L breaks that down, and M sub L breaks that down. Right, so allowed values. Negative L to positive L. And they have to be integers. You can't have a 1.2, right, or a negative 3.7. It's got to be a negative 3 or a 0 or a 1. We're treating 0 as an integer as well. So we can do this, gang. All right, so if L is 0, let's see. Negative 0 would be 0. Positive 0 would be 0. 0. All right? So M sub L is 0 only. Now, sometimes I put a little line through my 0 because I used to always confuse O's with zeros. So sometimes you'll see me do a 0 like that. Sometimes you'll see me do that for 0. It's just a personal habit that I've gotten into to make O's and zeros look different. So bear with me if I do that. Because if I do that, now it looks like one of those angles in the polar coordinates. I never thought about that before. So there's only one orientation, and we're going to do shapes in the next video. All right, so I'm just going to solve for them here. We'll do what that means shape-wise in the next video. So only one orientation for that. That's the only integer possible, which makes sense because 2 times 0 plus 1 is 1, so there's only one orientation of that. All right, so we can write that down here as well. So we have one value. All right, so number of values is 2L plus 1. So you can predict that ahead of time. So if L is 1, 2 times 1 is 2 plus 1, we have 3 values, which would mean 3 orbitals. If L is 2, 2 times 2 is 4 plus 1, so we're going to get 5 values, or there'd be 5 orbitals in a D subshell. And if L is 3, 2 times 3 is 6 plus 1 is 7 values. So maybe in introductory chemistry, they just had you memorize S sublevels have 1 orbital, P sublevels have 3 orbitals, D sublevels have 5 orbitals, and F sublevels have 7. 1, 3, 5, 7. They maybe just had you memorize it. But using quantum numbers and quantum mechanics, it comes from the mathematics, right? That's why there's 1, 3, 5, and 7. All right, let's solve what they actually are. Well, if L is 1, well, negative L would be negative 1. So M sub L could be negative 1, 0, and positive 1. There's our 3 values, right? Negative 1, 0, and positive 1. And so there's 3 ways to orient that particular shape. And we'll see you have the PX, PY, PZ when we do that. Well, let's look at the D sublevel. You should be able to pause this and do yourself. If L is 2, well, negative L would be negative 2. The next integer up would be negative 1. Add 1 each time. So negative 1 plus 1 is 0, positive 1, and positive 2. So if you want to look at this, this would mean we have 1 orbital. This means we have 3 orbitals, or 3 seats. Remember, the further out you get, the more space there is. So it does make sense. As you move farther out, higher n values, there's more sublevels. And the farther out you get, the bigger the sublevel, the more seats there are, right? So this would be 1, 2, 3, 4, 5. So this would be 5 orbitals. And we'll see in the next video the different types. Now we start getting crazy. You get these dx squared minus y squared and dz squared and dxy and dyz. Blah, blah, blah. It gets kind of kooky, right? These kind of look like 4-leaf clovers, most of them. And there's one that looks like a p orbital with a donut around its waist, like a p orbital with a hula hoop. It gets so fun. Now the F, that gets super F for freaky, man. All right, here we are. We got 7 answers. So if L is 3, well, negative L would be negative 3. Oh, let's get the right color. So M sub L could be negative 3, and just keep adding 1 until you get to positive L, or positive 3. So negative 3 plus 1 is negative 2. Negative 2 plus 1 is negative 1. Negative 1 plus 1 is 0. 0 plus 1 is positive 1. Positive 1 plus 1 is positive 2. And positive 2 plus 1 is positive 3. Good thing we don't really go past that. So that's 1, 2, 3, 4, 5, 6, 7 orientations for that shape. And we're going to that's many, many lobes. Very weird shape. So that is 7 orbitals. Oh, you know what? We got a little bit of time. Let's do maybe a practice problem where I make you think about the constraints of this, and then we'll call it a day, and we'll do the shapes in the next video. All right, this one makes you think a little bit. Gives you kind of a twist on it. typically you're going to do it like the last one. Here's the value of n. What are all the allowed values of L and M sub L? Or here's the value of L. What are the allowed values of M sub L? That kind of stuff, right? But let's say I give you 2 of the 3 quantum numbers. If I do that, you should be able to peg the third quantum number at least to a specific value or a range of allowed quantum values. So let's say you're in the 4th principal energy level or subshell, right? So n equals 4. I don't know what L is, but let's say M sub L, the angular momentum, not the magnetic quantum number. The magnetic quantum number, M sub L, is 2. So we've pegged those. We should be able to narrow down a specific value of L or a 2 or more allowed values of L. Pause the video, see you can do it, but see if you can do it. But the thinking process is, well, if n's 4, what are the allowed values of L? What's my range of L values? If M sub L is 2, what does L need to be to get me that? So you can kind of get a cap on the maximum size of L from this, and you can get a cap on the minimum size of L from that, and come from both the biggest and the smallest and constrain it in and cap it in. Pause it and see if you can do it. I'll go ahead and punch this out, right? So from n equals 4, L can be all integers from 0 up to n minus 1. So it can be 0, 1, 2, and 3. So it has a max. L max is 3. So the maximum value of L can be 3 given n equals 4. See the 4 values? 1, 2, 3, 4. Now let's take a look at the constraints of the angular, I keep wanting to call that the other one, the magnetic quantum number. So from M sub L equals 2, what do we know? Well, the M sub L values range from negative L to positive L. So if M sub L is 2, L has to at least be 2. 2 or greater, right? Because if I had an L of 4, I could have negative 4, negative 3, negative 2, negative 1, 0, positive 1, positive 2, positive, so any value of 2 or greater for L, you could get an M sub L of 2. So L could be 2 or 3 or 4 or 5 or 6 or 7. But the maximum here is 3. So let's look at this. So the minimum is 2, and the max is 3. Right? So minimum 2, max of 3. So that must mean L could be 2 or 3. Does that make sense? Yeah. It could be 2 or 3 given a value of 4, but of n of 4. But if M sub L is 2, it couldn't be 0, right? Because you couldn't get an M sub L value of 0 from that. I mean, if L is 0, yeah, you couldn't get an M sub L of 2 from that, right? Because it could be only 0. If L is 1, you could get M sub L of negative 1, positive 1, and 0, which is not 2. So it can't be this, and it can't be that. It has to be at least 2 and 3. So we get 2 possible values. But see how you constrain it? You get a maximum from the M value, and you get a minimum from the M sub L value, and you can figure out your L value from that. So as long as you got 2, you can usually figure out the third one. It's just playing with it. You're good to go. Let's do shapes on the next video. But I'm starving! Need a sandwich!